So we're going to continue with chapter 9, and we just barely started the topic on the effects of the Drd mismatch, essentially on the common mode gain or rejection of the differential pair. So the idea that we had essentially this type of configuration here. So we have here a bias current. So the idea of the result that we did finish that the output voltage, so taken from here, so this would be VO2, this one would be VO1, that the gain of each of the outputs, so the differential outputs, with respect to some common mode input was the same. And that was about, because if you recall, the term that showed up in the derivation to RSS, which was an abstraction of this current source, was much less than the GM of the transistor, the transconductance, and that reduced this gain to RD over 2 RSS. So the RSS being this abstraction here. And the idea is that that is valid. That is valid if these two resistors were matched. So we wanted to look at the effect, because that's not realistic, very theoretical, but not realistic. What was the effect of the mismatch of the RDs? So that's what we're going to look at, how these relationships change. So they're no longer the same now, because the RDs are not the same. So I cannot say that this is the case. So now I'm going to formulate each output voltage by themselves. So first, the first one, I'm going to say that that is minus RD over 2 RSS times the input common mode voltage. That's the first output. And then for the second, we're going to have RD, but we're going to add some delta because they are not matched. So we're going to allocate the delta to the second RD. And then we're going to take the differential output. So that's going to be minus, when you go through the difference of these two, minus delta RD over 2 RSS times the input common mode voltage. And then I can find a common mode gain. And that's going to be defined the common mode gain as the differential output voltage over that common mode input. And that's going to be from the previous expression, and that is also another way of writing that is minus Rd. If I introduce Rd again without changing the overall expression, and I see that the reason to introduce Rd again is to look at how that gain depends on the percentage of deviation of Rd, which is delta Rd over Rd. Then I can define a very important quantity, which is called the common mode rejection ratio, which relates the gain, the common mode gain, to the differential gain. And what I want is a very high value, a very high number. The way that we're going to define it, because we want the differential gain, which is what we want, to be much higher with respect to the common mode gain. Or another way of saying it, just that the common mode gain is much smaller than the differential gain that we want. So if you look at any data sheet for an op-amp, you'll see this specification. This is a design parameter for op-amps. And if we were going to do something for instrumentation or measurements where you can have a noisy environment and then the noise is common, so you want to suppress that or have a much higher differential gain for what you're measuring versus the gain of the common noise, then you would want a very high common mode rejection ratio. So that would make for a good op-amp for that application. So that's a parameter of op-amps that is in all data sheets. So we are going to define the common mode rejection ratio as the absolute value of the differential gain divided by the absolute value of the common mode gain.
Dr. Hernandez?
Yes.
Could you possibly let Josh Toby in from the waiting room?
Oh, sure. So that quantity, the common mode rejection ratio, can also be expressed, and actually that's how it is expressed in data sheets, is normally expressed in dB. So that's going to be 20 log of the differential gain, the ratio to the common mode gain. And if we go back to the previous expressions that we have derived and seen, the common mode rejection ratio, which is this quantity, the one that is not in dB. So this one is in dB, this is just this common mode rejection ratio here. That common mode rejection ratio, another way of expressing that is 2 times the transconductance times the source resistance divided by that percentage of deviation of the RD. That's what we introduced that term before. So that's how we put a measure. That's how we put a measure with these two quantities in the mismatch of the RD, and we can see it exactly what the effect is. So when we see that number in the data sheet, that is a worst case ratio that the manufacturer is standing by and saying, you know, our process is such that whatever mismatch on RD we have for biasing that input differential pair, we're not going to see a common mode rejection ratio that is lower than this. Okay, remember this is a high number. This is a high number, so you want the higher the better. So when it's guaranteed, it's guaranteed that it's not going to be lower. All right. So next, we want to keep looking at, in terms of the differential input pair, we want to keep looking at the effects of other non-idealities. Another effect that is, because throughout everything that we've been talking about, another assumption that we have been making, which is not unreasonable, because we can match the transistors fairly close with a very tight window of control, but they're not exact, and we want to know what the impact of that is. So another impact that is important.
Dr. Hernandez?
Yes.
I had a quick question about the AD over ACM. Did you, why wasn't AD defined as a GM times RD, or was there just some algebra that I'm missing out, which put the RD on the bottom of the equation and then the 2RS on the numerator?
Yeah, that's part of the algebra. You have to go back to the previous expressions. I didn't show it, but it will fold from the previous expressions. Like my notes is like a couple of pages before that. Okay. My assumption is, you know, you're taking notes along, and the idea of publishing the videos is that if for some reason, you know, you want to go back and contrast your notes to the video, you can stop the video, you can do all sort of things. But yes, you will see that will fall from the that will follow from the algebra. Okay.
Okay, perfect. Thank you.
Okay. So let's look at the effect of the transconductances of the pair of transistors that are not matched. So this is the effect of GM, because again, we were assuming that transistors are matched on GM, but the reality is that they're not. And what is the effect specifically of this mismatch on that very important common mode rejection ratio? So we can write the common mode gain, we can approximate it by now we're looking at if you wanted not to do work with deltas and you wanted to make a continuous or infinitesimal analysis, this is equivalent to taking partial derivatives for each of the quantities that you are looking at, and looking at the sensitivity of the quantity, in this case, the common mode rejection ratio, due to that specific parameter. So right now, we're going to keep the RD fixed, but we are going to say that there is a variation on GM. And the delta GM is essentially the difference between the two GMs of the transistor. Then in that case, similarly to the previous result, we see that the common mode rejection ratio can be expressed as 2GM times RSS times or divided by the variation. And that makes sense intuitively because essentially, if you have no variation, then this term is 0, which would make the rejection infinite. So it would be a perfectly matched differential input pair, and you will not amplify any of the common mode signaling. So ideally, that's what we started with, but now we're saying that's not the case. It's going to be a finite number because the ratio, the delta, is not going to be 0, although it's going to be very small, and it's going to make this quantity very small. It's going to make the common mode rejection ratio very, very large. But it's not going to be, this ratio is not going to be 0, as we first assume in an ideal world. All right. Now, as we keep building this op-amp, we're going to put, we know that the op-amp has two inputs, and they're going into this input differential pair. After that, we're going to have gain stages, and later on, we'll put together the whole thing. But those gain stages are single-ended. They are not differential. So we are going to have, a way, a mode or a method to convert that differential output that the differential input pair gives us to a single-ended, what is called a single-ended signal. And we're going to see that we have to do that because we cannot keep operating differentially. As you know, that the op-amp eventually has an output that is single-ended. Most of them, we could do a fully differential amplifier. That's not what we're doing. That's a little bit more complex. So we're doing basically your plain op-amp with two differential inputs, one single-ended output. So at some point, we have to convert from differential to single-ended. And the big drawback of doing that is that the common mode rejection ratio is reduced greatly, unfortunately. And that's for very high-end, high-precision type of applications. Although they are more expensive and complex, you have a fully differential op-amp that has a differential output. Those do exist. But we're going to look at the effect of converting to single-ended on the common mode rejection ratio. So let's look at that as another reality, because most op-amps are single-ended outputs. So let's look at differential versus single-ended and what we're going to see is that the common mode rejection ratio is reduced. So let's start with our common mode gain that we found. and also our differential gain. And if we do the ratio, then which is much smaller than, this is due to the single-ended conversion, which is going to be much smaller than the following. So these two things are connected, but I need to make space for that. So the previous, well, let's just do it again here. That's going to be much smaller than this expression. And what we're doing here is taking both variations due to GM and Rd mismatch and just averaging it. That's just averaging the variations. When we have a differential output, this expression is valid. So this is differential output. This one is the reduction due to single-ended. And if you just look at the quantities, you'll find that this GM times RD is much smaller than this one. So you can start seeing where the non-idealities come from, essentially from not being able to match the transistors. And we want to keep looking at those, and they're all in the data sheet of op-amps. So the next one that we're going to look at, and again, this is in the data sheet of op-amps, the next non-ideality is offset voltage. So if you look at a data sheet of an op-amp, another characteristic or another metric is the offset. And we're going to look at it first. And this is the output offset due to, just like we did, first due to the Rd mismatch. For that, I want to show figure 927, which the analysis is going to be based on. So just to, there is nothing new really in this figure, but I guess I don't really need to show it. All we're doing is taking the same differential pair And the idea is that or actually this could be and the idea is that if you ground the inputs and you take the output, the outputs. So here you have your output. This is Q2, Q1, and you have another output of here. And you take the output from there. If the RDs are matched and everything is matched, actually, if you have with this situation where you have the differential input obviously 0, your output should be 0. Your differential output should be 0. But it's not in the non-ideal world that the RDs are mismatched, and later we're going to see, just like we did before, for the common mode rejection ratio, when the GMs are not matched. So those two, the main mismatches of transistors, are going to contribute to us having a non-zero output, differential output at the output of the differential pair, which then will be carried over all the way to the output of the op-amp. So that's what we're going to be discussing, okay, based on this. So the first thing that we're going to do is say, for transistor 1, RD1 is going to be some nominal value of RD plus some deviation from that value divided by 2. And for transistor 2, the RD is going to be some nominal value minus half the deviation. So essentially, we are allocating half the difference between the RDs to each of the RDs. And if we go with that, I can also write a drain current for transistor 1. That's going to be the bias current divided by 2 minus GM times the offset voltage, because the drain current gives me the offset voltage as it develops that voltage across RD. And then the current in drain 2, similarly,
Dr. Hernandez, is the offset voltage over 2 multiplying just GM or the entire thing?
just GM.
Okay.
So this is the term. So you can see from these expressions that if you wanted the output voltage to be 0, if I want the output voltage to be 0, the voltage due to the, or developed by those currents across the RDs, the drain resistors, have to be the same. And that's what I would like to have, okay? In that case, I can write this this expression. Essentially, the voltage across the drain resistor so essentially, I'm looking for what is the voltage that I need to nullify the offset, which is essentially saying what is the offset. So this is the current here. And now this is the RD with the built-in differences. And that's going to be, so this first expression is for Q1, and now for Q2, I have a similar expression. And again, if you go through some algebra and solve this expression for the offset that you want to find out, which is your nullification voltage to make the output 0, which is what you want, you find that the offset expression is the bias current divided by 2 divided by GM times the difference or the percentage difference of the RD. So again, it makes sense intuitively that if the deviation or the difference or the mismatch of RD is small relative to the value of RD, then the offset is going to be small because they are directly proportional. Now, GM is equal to the bias current divided by the overdrive voltage, which makes this expression here. So this we knew, we've been looking for this, saying that the overdrive voltage, the voltage offset at the output of the differential pair is proportional to the difference as a percentage of the deviation with respect to RD, but also the offset now has this component of the overdrive voltage. For a number of reasons, I would like to have a large overdrive voltage because it gives me more output and also a larger noise margin. But that is counter to having a small output voltage offset. So those are conflicting requirements. So as part of designing an op-amp, I'm going to have to look at what is the optimization point between the overdrive voltage at which I operate, or the range of overdrive voltages that I operate at, and the output offset voltage. So that's good insight there. Okay. So these are all not just, so these equations are not just for the sake of memorizing them, because I don't expect you to, or so much as calculating things, but these are so you can see that the design principles and doctrines and the knowledge that you need to have to design good op-amps are governed by the mathematics behind it, and they have to do with the issues of mismatching the transistors, which are real. All right, so let's look at another quantity that can introduce or can contribute to the output offset. So here we're also going to look at offset due to the K of the K mismatch of the transistor. And the main contributor to this mismatch is the geometry. We're not going to get exactly each transistor fabricated with the same channel length, with the same channel width. So that's going to be the main contribution there. But we're going to lump all that into a variation of the K. Although those are the main contributors, where the mobility is going to be the same because it's the same material. The oxide properties are going to be the same. It's going to be the oxide, but there could be some minor variations on the oxide, but mainly it's because of the geometry, being able to match the geometry, which is what we want. So we're going to express the K for transistor 1 as same as we did with the RD. So nominal K and for transistor 2, so nominal K minus half the variation or the difference between the Ks. And then we're going to do the same. We're going to have to apply that to the drain current equation. And what that says is that even if you match the RD, since you cannot match the Ks, you still have some contribution to the offset. Okay? So let's look at that by itself. Let's say we could match the RDs, but what happens to the voltage offset due to the mismatch on the Ks? So let's make a note for ourselves here that even and the equivalent of matching the RD is when you bias the transistor is making those current sources or current mirrors perfectly match themselves. Remember that we really don't have a resistor there. Those are biased networks. So we do the same thing. We say, what is the offset value or the value to nullify the offset, which so the offset now, we're going to take it as the value to nullify the offset, to make the currents the same. And that happens when when GM times that voltage by just looking at one side of the differential pair. So that happens when that expression is true. So essentially, I get exactly the same currents, and then I can solve this expression for VOS, and that would give me that voltage, and that is then I'm going to substitute. So I'm going to substitute GM for its value. And then I can have the offset, that offset voltage very similar result than what we got before. So again, even if the RDs are matched, I have that dependence on the variation of the case. Even if the case are matched, I'm going to have the dependence because of the RDs, but always in both cases, the offset voltage is going to be dependent on the overdrive voltage, which I need. So what that says is that every op-amp is going to have some type of offset. You cannot really, on the design alone, you cannot get rid of it. Now you can put extra circuitry to actually nullify that offset, and some op-amps have actually extra ports or extra pins, if you're thinking of a chip, where you actually can put a resistor across it and like a trim pot and actually nullify the offset. But on this guy, always going to have an offset, and then you can put circuit inside and have another 2 ports that help you make that 0 on the actual application. And if you have a very critical application, you may have to do that independently for each circuit. So here you have some variable resistor that you can essentially dial in to make that. What you would do is you would tie these two together, and then, oops. Let me draw that again. So basically, you would have some type of port here, and you would tie the inputs together, and you would you would dial this variable resistor until the output is 0, and that nullifies that offset. But as a 3-terminal device, you will always have an offset because it's dependent on the overdrive voltage. Let's now take a look at another quantity, which is that can contribute or contributes to the offset. And again, all the data sheets is going to have the offset Always worst case. The manufacturer always going to quote worst case, and is going to guarantee that it's not going to be larger than that, because this is a quantity that you want to have as small as possible. So another contributor to the offset is due to the mismatch of the threshold voltage. Another quantity that can be where there can be mismatch when your intention is, or your desire is, to match the resistors. So again, let's go through the same type of analysis and say that for transistor 1, the threshold voltage is a nominal value plus some variation divided by 2. And for transistor 2, and now let's look at the drain current expression that involves the threshold voltage. So for transistor 1, we hold the K the same, but now we're going to see what happens with the threshold voltage. And if we expand the quadratic term, we get this expression. And also we introduced a VGS minus VT term here. And then let's substitute because that's the overdrive voltage. And let's also assume, which is not unreasonable, that variation in threshold voltage is much smaller than 2 times the overdrive voltage. To simplify the expression, it helps. So he says that it helps to make the overdrive voltage, but we know that in other contexts, having a larger overdrive voltage is going to contribute to the offset as well. So you can see how all these parameters and requirements can conflict each other. And the designer's job is to find the best mix of the best design that optimizes overall, and look at how all those parameters affect each other without taking forever. So, because perfection cannot be the enemy of the good, cannot take forever. So, if that's the case, I can write that expression or approximate it as this. And then what happens is that the quantity 1/2 the K times the overdrive voltage square is the drain current. So remember that we're looking at 1/2 the differential input pair. So it's the bias current divided by 2 because the inputs are 0. They're tied to the gate. I mean, the gates are tied to ground. So if I put this expression into here, ideally, I want this quantity, which intuitively makes sense. I want the drain currents just to be exactly 1/2 of the bias current I. So I want this expression to be 1, which implies that I want this to be 0, which implies that I want delta VT to be 0, which implies that I have matched the transistors perfectly. So the expressions match the story of what we want. So now we have this expression, and that gives us that current for the transistor 1/2 of the circuit. And we can go through the same thing and get the current for transistor 2, the drain current for transistor 2, or I can just realize that the current for the drain current for transistor 2 is the bias current minus the current for the drain current for transistor 1, because these two currents come together as the bias current I. And also, remember that I have the gates tied to ground. This is where the differential voltage, input voltage being 0. So if I do this subtraction, I can get the drain current for the transistor 2/2 of the circuit and get a similar expression. Now that I have the currents, I pose the same question. Because if the currents are the same, and I'm just to look at the variation for the threshold voltage, I'm holding the fact, or I'm assuming that there is no variation on the drain resistance. So now they're the same. And if the currents are the same, then the output differential, the differential output voltage is going to be the same. And that's going to be the voltage that it takes for that to happen is going to be my offset. In this case, due to the variation on VT. So it's equivalent as just looking at the partial derivative of VT. But in this case, a little bit different because it's relative to the overdrive voltage, which is more convenient. So, so to do that, to find that offset that makes the current the same, such and also GM in that case if you equate the current if you use this expression and equate the equation of the currents, you find that that offset voltage so if we substitute GM that we had before, okay? So the GM, again, I'm just gonna write it again. And you put that in there, you get VOS equal to just the difference on threshold voltage. So we have seen three effects for the output offset voltage due to the difference on the RD, due to the difference on the Ks, and due to the difference in VT. So we have expressions for that. And we can, one way to bring all that together, because we looked at it as a partial, in the spirit of a partial derivative type of analysis. But we can bring all that together because the reason we can look at it independently is because these effects are not correlated. You could have some change on K, and that is not going to be correlated at all with the change on VT or the change on the RDs. These are different parts of the circuit and different parts of the construction of the transistor that contribute to these changes. So I'm going to say that since the sources of the offset are not correlated, I can find the overall offset from all the contributions. And I do that by, since there is no correlation, by taking the Euclidean distance. Or norm. So then my total offset due to all the effects are the first one due to the mismatch on the RD. So that was, if you recall, the overdrive voltage divided by 2 times the change then the one due to the Kn change or variation or mismatch, and the one due to the VT change, which is just the mismatch. And then that would be the Euclidean norm. So due to mismatch on RD, due to mismatch on K, and due to delta, to mismatch on threshold voltage. All right, so Now that we understand all these effects, let's look at the actual conversion from differential to single-ended output using a current mirror load. So let's see if we what we're going to do. Now, to base that discussion, we're going to use figure 931 of your book. So here, we're going to load a differential pair with a current mirror, and we're going to take the output, a single-ended output from this, from the Q2 half of the differential pair, okay? And the rest of the figure just goes through some of the, or all of the quantities that we're going to be discussing next. So while you're doing that, while we're going through this, keep looking at this in your books, okay? We're going to start here, and we're going to see what the outcome of that analysis is and how we convert the differential output to a single-ended by loading the differential pair with a current mirror. So this is the circuit we're talking about here. So let's do that. So the first thing that we want to, and actually the book goes to the derivation of these quantities that I'm going to state. I'm not going to go through that, but the book does go through it. So I refer you to the derivation of these quantities. The first one is what we are going to call the short circuit transconductance. So what happens when I short the output? And I'm going to call that capital G, GM, which again, assuming that transistors are matched, is going to be the GM of the transistors. Also, the load is going to be, since now the load or the output is going to be on the Q2 side that has Q4 on top as part of the current mirror, the RD is going to be, for the purposes of the discussion here, the output resistance of transistor 2 in parallel with the output resistance of transistor 4. So that is the right side of the circuit, those two transistors. Okay? And So this is the differential pair, and this is the mirror part. Let's see if it would help to show something else. So if you apply this to the transconductance and this to the output resistance, this is not RD. Looked like a D, but it's not. It's not. I want you to make that distinction. That's not an RD. That is an O for output. Okay. For the purposes of this short circuit calculation of how I can translate to from differential to single-ended, I want this whole circuit to look like a single transistor. And to do that, the derivation that is in the book that I didn't do is that for that abstraction, I'm going to have this GM, which is really going to be the GM of the amplifying transistors, the bottom two, the differential pair, and then an output resistance that is the parallel combination of the two transistors on the right, where the output is being taken. And that is the differential transistor and the current mirror transistor 4. So differential was transistor 2, or is transistor 2, and the current mirror transistor is transistor 4. So now I can abstract those 4 transistors, or the differential pair loaded with the current mirror, as a single transistor, which is going to look like a transconductance, the one that I found here, that abstraction, times the differential input voltage. And then here, I'm going to have this here is going to be the RO that I found, that abstraction. And then at this node, I'm going to have my single-ended voltage. So now I know that what my output voltage is going to be, because it's going to be this current times that resistance. And now I can define a differential gain that is going to be the single-ended output divided by the differential input. And you can see that that's just going to be given that circuit that I just drew. And if we go back to relating those quantities to the actual transistor parameters, that's going to be the GM for the differential pair transistors times the output resistance for transistor 2 of the differential pair in parallel with the output resistance of transistor 4 for the current mirror. And another way of writing it is that the output, because the transistors are matched, both transistors in the differential pair are matched, and both transistors on the current mirror are matched. I can say that this is the output resistance of the differential part in parallel with the output resistance of the mirror part. That's another way of looking at it. Some last observations. So transistors are matched, so I can just write GM, and if I further match the differential pair with the current mirror, then I can say that these two output resistances are the same, and I can call that just RO. So this is if all transistors are the same or matched. And then that gives me a differential gain with the differential to single-ended conversion taken into account of 1/2 GM RO, which is 1/2 the intrinsic gain of the amplifier, which is just GM RO. So by converting the output from differential to single-ended, I give up half the gain essentially, and that makes sense because I'm throwing away the other half of the differential output essentially. So that's what this says. So if I continued processing the signal differentially, then I would have more dynamic range, but that would make my circuit more complex and more expensive. So I can get back some of that gain later with subsequent stages of amplification. And that's where we're going to go next and talk about, without a lot of derivation, just talk about the multistage amplifiers. And what we'll see is that the voltage gain, and I'm going to show you specifically which multistage amplifier we're talking about in the context of building the op-amp. So stage 1 and there is going to be a stage 2. So the gain for a stage 1 is going to be the transconductance of transistor 1 times the output resistance of transistor 2 in parallel with the output resistance of transistor 4. So that's going to be a differential input pair loaded by a current mirror. So the subscript, the numbers in the subscripts refer to the actual transistors numbers in the circuit that I'm going to show you next. So keep that in mind. And then the second stage gain is going to be the transconductance of transistor 6 times the output resistance of that transistor in parallel with the output resistance of transistor 7. So the circuit that refers to this gain expression for each of the stages, and then of course the overall gain is just going to be A1 times A2, is going to be a common source. So the gain for A2 is going to be from a common source loaded with a PMOS current source. So again, going back to the actual schematic that this expression is referred to, let's look at it. And here you have it. This is the simplest op amp that you can have, and it is used. And here you can see now this op amp is flipped. Okay, so here you have your single bias current at the top as a on the P channel network. So I know that you've been used to seeing the I with the current source at the bottom, but these topologies are symmetric. You can flip them from N to P and vice versa. So here we have the bias current with the P channel current mirror here, and you're used to seeing the reference current, the reference resistor on the top of the current mirror. Now we have it at the bottom towards VSS, but nothing has changed. And here you have the current mirror that is loading the differential pair to convert from differential to single-ended here at node D2. So it's essentially what we have been seeing is just being flipped from top to bottom, okay? And here, this current mirror also is developing a bias for Q7 that is acting as a dynamic load for a current, for a common source amplifier Q6, which is the second stage. So again, A1 in the expressions that I wrote before is the differential gain between the inputs of Q1 and Q2 converted to single-ended at this node. And then here we drive the common source Q6, which gives us the gain for stage 2 as it's loaded by Q7. And here we have the output of the whole thing. So I could say that VO divided by the differential input of the gate at the voltage, the voltage at the gate of Q2 minus the voltage at the gate of Q1 is equal to A1 times A2. And those are the expressions that I wrote before I switched screens. So this is a two-stage simple op amp. The only thing is that I haven't told you about is this capacitance. So here's, and if we can get into it, we'll do so. I'm not sure, but there is a frequency analysis that needs to be done that we haven't done. We've done DC analysis and a small signal analysis, but we have not done a frequency analysis. And if we did that, we will find that to make this circuit stable and by introducing a pole, I need to have this compensation capacitor. So that's what is CC the subscript C stands for compensation. That is a compensation capacitor that sets that pole that all op-amps have, and that also gives you the bandwidth, the gain bandwidth product. So that's a subject of the frequency analysis chapter, which I'm not sure if we'll get to, but you always have this compensation capacitor. And the nice thing is, because of something called the Miller effect, that capacitor, even though small, it looks like much larger because of the gain. And that's called a Miller effect. But again, that's discussed in that chapter of frequency analysis. Hopefully we can get to it. I'm not sure. But that we'll talk a lot more about that capacitor in that chapter if we get to it. If not, then at least you sort of know why it's there. But it's necessary to make the circuit stable, and it's always there in op-amps. And it sets the gain bandwidth product or the pole of the op-amp. All right, so this ends chapter 9.